In this video, we will be talking about the Nicolson method for finite differencing. As shown in the previous video with the von Neumann stability analysis, our equation is not stable for any r greater than 1/2. So the goal is to demonstrate stability for any r. The Nicolson method is a little different because you take more time intervals and average them. So it will be very similar to the math we've done before with just a couple of slight changes. So to start, we have our equation that we have seen multiple times at this point. So the change in temperature over the change in time times the heat diffusivity constant and the change in temperature with respect to position. So we have the same notation of TJN with position and time intervals. So we will have TJN plus 1 minus TJ of n over delta T for our change in temperature with respect to time. And then we have our heat diffusivity, and then we have the change in position that we have seen several times as well. I'm going to go ahead and pull out the delta x squared that would be in there. And then because we want to have multiple time intervals, we need to go ahead and do one further time interval and then average them. So that would be plus TJ to the n plus 1. So all the same, just n plus 1 for the next interval. And then we would divide this by 2. I'm going to go ahead and throw it in over there just for simplicity. We'll start simplifying with algebra as we have done previously. So we're going to go ahead and make this an r term again. The only difference is there's also a division by 2. But it's still constant, so we can still put it as r. So we'll have TJ n plus 1. So these terms do not simplify because they are at different time intervals, but we can simplify by putting all of the time intervals of n plus 1 on the left side and all the time intervals of n on the right side. So I'm going to go ahead and do that. Alright, so we can go ahead and start simplifying this even further. Now we can kind of work on simplifying. So this is a t of j, this is a t of j, this is a t of j, and and this is the t of j, so we can write that as 1 plus 2r to t j n plus 1 minus r t j plus 1 n plus 1 minus r t j minus 1 n plus 1 is equal to 1 minus 2r t j n plus r t j plus 1 n plus r t j minus 1 n. So this is as simplified of an equation as we can get, but we're going to work in Google Colab Python to further analyze this using tri-diagonal matrices. So that's pretty much, we're going to have 3 matrices. We're going to have 2 on the left-hand side and 1 on the right-hand side. So to start, this is going to be our kind of our t column, so it'll be t of j equals 1, t of j equals 2, t of j equals 3, and so on till we get to t. And this is not in the matrices, because if we, to go back a step, if we look back at our linear bar in our segments, we have t of 0 and t of n. And at t of n, it's 400 Kelvin always, and at t of 0, it's 350 Kelvin always. So these aren't changing with respect to time, so they aren't in the matrices, but we will still have to account for them. So t of n is equal to 400, and t initial is equal to 350 Kelvin. So if we're looking at this, this is kind of the main variable. And then we have in here, if we're looking at our matrices at j equals 1, we're on the left side of the equation still, so we are referencing this part. If you plug in 1 would go right here. There's not really a 0th spot in a matrice, so if you plug in 1, the coefficient of t of j equals 1 is 1 plus 2r. And then if you plug in 1 into here, it'll give you the second value, which is coefficient of negative r. And then if we don't have a plus 2, so these will be zeros. We're just going to go to 4, but it's really indefinite. And then if we look at t of j equals 2, t of j equals 2 would go in the second spot, so the 1 plus 2r goes in the second slot. But if we plug it in here, t of j equals 2, 2 plus 1 is equal to 3, so it kind of goes in this third spot. It's negative r with a 0, but we also can plug it into here now, and we'll have the first spot is also negative r. And if we look at this, it's going to just continue down these diagonals, this pattern, and then over here it'll be a 0, and that'll continue, and a 0, and a 0, until we fill in this matrice. And then similarly on this side, it'll be 1 minus 2r, and then it's t of 1 to the n, and then t of 1 to the n plus r t of 2 to the n plus r t initial to the n. And then we would just continue this as well throughout the matrice, plugging in our t of j values, and we'll look at that further in Google Python. Okay, so we're going to work on the Python for the Crank-Nicolson method to demonstrate any value of r and work on the instability of the finite differencing equation. To start, we're going to do similar imports as last time. And then I'm going to add this this command. We're going to import solve banded, and that's something that you can look up on Google, but pretty much it's a way to import matrices into oops, I put a Y instead of a G. Oops. Into Python. I need a G. All right. Okay. And then we're gonna again just put in our variables. I'm just going to go ahead and make r equals to 1 because that's above our 0.5 from last time. So we're going to keep a space just for it to match. T is the same. With the same 300 initial temperature of the entire bar. And then the 350 on the left and the 400 on the right. And X is the same. All right, so now we're going to start inputting our matrices, and I will explain after I type this out a little bit. So what this is this is our, we kind of talked about this just a minute ago on the whiteboard. This is our leftmost matrices, and it's there's like the three, and then this is the number of divisions minus 2, and the number of divisions minus 2 is because of that constant on either side. We don't want those two divisions, so the matrix C will be comprised of everything but those two. And then like the initial was the negative r, it was the j minus 1, oops, it was the j minus 1 that we mentioned in the previous video. The 1 is that 1 plus 2 times r, which was the j equals 1, and then the 2 is negative r again from the last part of the video. And then we're going to work on our next matrix C. It's an x minus 2 again, but this is just one column, so we don't need the 3. And then b is equal to the r times t plus 1 minus 2 times r times t, 1 to negative 1 plus r times t, and then 2, negative 2. And this is from that last video as well. We kind of talked about it. It's the right hand side of the equation. So b initial is equal to that b initial plus r times capital T initial. And then the b negative 1 is equal to b negative 1 plus r times t of negative 1, and these values are those initials, the 350 and the 400, since those aren't changing, you know, they weren't in this area, so we have to account for them somewhere. We're going to make a figure just to show our initial conditions. All right, and then big 2, add scatter. This is the same syntax as last time. Nothing's really changing here. And it's gonna be named initial again. And we're gonna hope the syntax is good. Let's see. Let's add some spacing. Oh, I forgot the 2 on this one. Let's see if that fixed it. All right, so that's our initial that we saw. This is like the first time step that happened. So then we're going to, as we talked about in the video, you have to like do the average. So this is kind of that first one we're going to use to do the average. So then we need to do our for loop again to get the other values, similar to last time. So it's going to be our matrices. And this is just the syntax that you could kind of look into a little bit further. And then I'm going to go ahead and copy our looped values that we want. We want all of these in our loop because it'll have our output. We need to enter these in or they won't be in the loop. And then we're going to kind of complete our loop again. If 5% 100 equals 0. Then we're going to do the big2 dot add scatter x equals x, y equals t, mode equals lines. And then this one we're going to name with these like squiggly brackets because it'll put whatever loop we're on in the name, which is what we want, so we know which iteration we're on. And then fig2 dot show, and this should look really similar to the other temperature graph before the R became unstable. Yep. And just a reminder, we did have an R value of 1, which is above that 1/2. So we are demonstrating that with the Crank-Nicolson, we can work on that instability a little bit, but it's like the first time iteration, then the second time iteration, and then this average of those time iterations, and as we continue on. And yeah, so we definitely improved the stability of the equation with this method.